For power monitoring in residential buildings using an Ethernet-based system, consider solutions like the Power Insight system from Elster Metering. This system uses existing Ethernet infrastructure, which can reduce installation costs compared to running serial cables. You may also consider using the Direct Energy software solution for calculating power quality parameters. The Power Insight system provides a way to monitor power consumption within the buildings. It's important to select a system that not only monitors but also provides the necessary data for billing and analysis. Power monitoring systems generally consist of several key components. Firstly, current transformers, or CT. These devices measure the current flowing through the electrical conductors and provide a signal to the monitoring device. Secondly, voltage transformers, or potential transformers, for PT. These devices measure the voltage of the electrical system and provide a signal to the monitoring device. Thirdly, a monitoring device. This device collects the signals from the CT and PT and calculates various power parameters such as voltage, current, power factor, and energy consumption. Fourthly, a communication interface. This interface allows the monitoring device to communicate with the central server or software for data logging and analysis. Fifthly, software. This software collects data from the monitoring devices, stores it in a database, and provides tools for analysis, reporting, and billing. When selecting a power monitoring system, consider the following factors. 1. The number of points to be monitored. Determine the number of electrical circuits or loads that need to be monitored. 2. The accuracy required. Select a system that provides the accuracy required for billing and analysis purposes. 3. The communication interface. Choose a system that uses a communication interface that is compatible with your existing network infrastructure. 4. The software features. Select software that provides the features you need for data analysis, reporting, and billing. 5. The costs. Compare the costs of different systems, including the cost of hardware, software, and installation. For calculating power factor, the system should be able to measure both active power, also known as real power, and reactive power. Active power is the power that performs actual work, while reactive power is the power that is stored and released by inductive and capacitive loads. Power factor is the ratio of active power to apparent power, which is the vector sum of active and reactive power. A power factor of 1 indicates that all the power is being used effectively, while a power factor less than 1 indicates that some of the power is being wasted. To calculate power factor, the system typically uses the following formula: power factor equals active power divided by apparent power. The system measures active power in kilowatts or kilowatts and apparent power in kilovolt amperes or kilovolt amperes. The system should also be able to track peak consumption, which is the highest level of power demand during a specific period. This information is important for understanding the overall load profile and identifying opportunities for energy savings. The system should record the date and time of the peak demand and the corresponding power level. For common area billing, the system should be able to allocate energy consumption to different tenants or areas based on their actual usage. This typically involves installing sub-meters for each tenant or area and using the software to calculate the energy consumption and billing amounts. The software should provide features for setting billing rates, generating invoices, and tracking payments. When selecting a system for common area billing, ensure that it complies with local regulations and metering standards. Consider the following key power quality parameters: voltage, current, power factor, total harmonic distortion or THD, and frequency. Firstly, voltage. The system should measure voltage accurately and provide alarms for overvoltage and undervoltage conditions. Voltage fluctuations can damage equipment and cause performance problems. Secondly, current. The system should measure current accurately and provide alarms for overcurrent conditions. Overcurrents can damage equipment and cause fires. Thirdly, power. The system should measure active power, reactive power, and apparent power. This information is important for understanding the overall load profile and identifying opportunities for energy savings. Fourthly, power factor. The system should calculate power factor and provide alarms for low power factor conditions. Low power factor can increase energy costs and reduce the capacity of the electrical system. Fifthly, total harmonic distortion or THD. The system should measure THD for both voltage and current. High THD can damage equipment and cause performance problems. Sixthly, frequency. The system should measure frequency accurately and provide alarms for frequency variations. Frequency variations can cause equipment malfunctions. Some systems also offer wireless mesh network options for power monitoring. These systems can be useful in situations where it is difficult or costly to run Ethernet cables. However, wireless systems may have limitations in terms of range, reliability, and security. Ensure that the wireless system uses a secure communication protocol and has adequate range to cover the entire area being monitored. When evaluating software solutions, consider the following features: data logging, reporting, alarm management, trend analysis, billing, and web access. Firstly, data logging. The software should be able to log data from the monitoring devices at regular intervals and store it in a database. The data should be easily accessible for analysis and reporting. Secondly, reporting. The software should provide pre-built reports for energy consumption, power factor, peak demand, and other key parameters. The report should be customizable and exportable to various formats. Thirdly, alarm management. The software should provide alarms for abnormal conditions such as overvoltage, undervoltage, overcurrent, and low power factor. The alarms should be configurable and provide notifications via email or other channels. Fourthly, trend analysis. The software should provide tools for analyzing trends in energy consumption and other parameters. This can help identify opportunities for energy savings and optimize the performance of the electrical system. Fifthly, billing. The software should provide features for calculating energy consumption and billing amounts for different tenants or areas. The software should be able to generate invoices and track payments. Sixthly, web access. The software should be accessible via a web browser, allowing users to monitor and manage the system from anywhere. When selecting a system, it is important to consider the accuracy of the meters and sensors. Meter accuracy is typically expressed as a percentage of the full-scale reading. For billing purposes, it is generally recommended to use meters with an accuracy of plus or minus 1% or better. The system should also be able to compensate for temperature variations and other environmental factors that can affect meter accuracy. In addition to the initial cost of the system, it is important to consider the ongoing maintenance costs. These costs may include calibration, repairs, and software updates. The system should be designed for easy maintenance and troubleshooting. It is also important to have access to technical support in case of problems. When installing the system, it is important to follow all applicable electrical codes and safety regulations. The installation should be performed by a qualified electrician. The system should be properly grounded and protected from surges and other electrical disturbances. Before commissioning the system, it is important to verify that all the meters and sensors are properly connected and calibrated. The system should be tested to ensure that it is accurately measuring and reporting energy consumption and other parameters. The system should be integrated with the existing building management system or other systems to provide a comprehensive view of energy usage. This can help identify opportunities for energy savings and improve overall building performance. The system should be used to track energy consumption over time and identify trends. This information can be used to set energy reduction targets and measure progress. The system should be used to identify and address energy waste. This can include fixing leaky faucets, turning off lights when they are not needed, and optimizing the operation of HVAC systems. The system should be used to educate tenants and building occupants about energy conservation. This can include providing information on energy-saving tips and promoting energy-efficient behaviors. Power monitoring systems are valuable tools for managing energy consumption and reducing costs in residential buildings. By selecting and implementing the right system, you can gain valuable insights into your energy usage and take steps to improve energy efficiency. In addition to the specific systems mentioned, there are many other power monitoring solutions available on the market. It is important to research and compare different options to find the one that best meets your needs and budget. Consider the specific features and capabilities that are important to you, such as the number of points to be monitored, the accuracy required, the communication interface, and the software features. Read reviews and testimonials from other users to get an idea of the system's performance and reliability. Contact the vendors and ask for demonstrations or trials to see the system in action. By taking the time to carefully evaluate your options, you can choose a power monitoring system that will help you save energy, reduce costs, and improve the sustainability of your residential buildings. The selection of appropriate current transformers or CT is critical for accurate power monitoring. CT are used to step down the high current flowing through electrical conductors to a lower level that can be safely measured by the monitoring device. The selection of CT depends on the maximum current that is expected to flow through the conductor. It is important to choose CT with a current rating that is slightly higher than the expected maximum current to avoid saturation. The accuracy of the CT is also important. CT with higher accuracy will provide more accurate measurements of current and power. The burden rating of the CT must be compatible with the input impedance of the monitoring device. The installation of CT must be done carefully to ensure accurate measurements. The CT must be installed in the correct orientation and must be securely connected to the conductors. Voltage transformers or potential transformers or PT are used to step down the high voltage of the electrical system to a low level that can be safely measured by the monitoring device. The selection of PT depends on the voltage of the electrical system. It is important to choose PT with a voltage rating that is slightly higher than the expected maximum voltage to avoid saturation. The accuracy of the PT is also important. PT with higher accuracy will provide more accurate measurements of voltage and power. The burden rating of the PT must be compatible with the input impedance of the monitoring device. The installation of PT must be done carefully to ensure accurate measurements. The PT must be installed in the correct orientation and must be securely connected to the conductors. The communication interface allows the monitoring device to communicate with a central server or software for data logging and analysis. Common communication interfaces include Ethernet, ARS-485, and wireless. Ethernet is a popular choice for power monitoring systems because it allows for high-speed data transfer and easy integration with existing network infrastructure. ARS-485 is a serial communication interface that is commonly used in industrial applications. Wireless communication interfaces offer flexibility and ease of installation, but may have limitations in terms of range, reliability, and security. The software is a critical component of the power monitoring system. The software collects data from the monitoring devices, stores it in a database, and provides tools for analysis, reporting, and billing. The software should be user-friendly and provide a variety of features to meet the needs of different users. Some software packages also offer advanced features such as predictive analytics and energy optimization. Alarm management is an important feature of the software. The software should provide alarms for abnormal conditions such as overvoltage, undervoltage, overcurrent, and low power factor. The alarm should be configurable and provide notifications via email or other channels. Trend analysis is another important feature of the software. The software should provide tools for analyzing trends in energy consumption and other parameters. This can help identify opportunities for energy savings and optimize the performance of the electrical system. The software should be able to generate reports on energy consumption, power factor, peak demand, and other key parameters. The report should be customizable and exportable to various formats. For common area billing, the software should provide features for calculating energy consumption and billing amounts for different tenants or areas. The software should be able to generate invoices and track payments. Web access is a convenient feature that allows users to monitor and manage the system from anywhere. The software should be accessible via a web browser. Data logging is a fundamental requirement of a power monitoring system. Data must be logged frequently enough to capture essential energy data and identify problems, but not so often as to overwhelm data storage resources. The rate of data logging should be adjustable based on the application. Data logging frequency can range from every second to every hour, depending on the level of detail required. An important standard to be aware of regarding meter installation and safety is the National Electrical Code, or NEC. Article 220 covers branch circuit, feeder, and service calculations. Article 230 covers services. Article 240 covers overcurrent protection. Article 250 covers grounding and bonding. Article 300 covers wiring methods. Article 310 covers conductors for general wiring. For example, NEC Table 310.15b16 details the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current carrying conductors in a raceway or cable or earth directly buried, based on ambient temperature of 30 degrees Celsius. The table provides ampacities for various conductor sizes and insulation types. Always consult the latest edition of the NEC and local codes for specific requirements. The Institute of Electrical and Electronics Engineers, or IEE, also publishes standards related to power monitoring and power quality. IEE Standard 519 provides recommended practices and requirements for harmonic control in electrical power systems. IEE Standard 1159 provides recommended practice for monitoring electric power quality. These standards can be helpful in designing and implementing a power monitoring system. In addition to measuring basic parameters such as voltage, current, and power, some power monitoring systems can also measure more advanced parameters such as harmonics, transients, and flicker. Harmonics are distortions of the voltage and current waveforms that can cause problems with sensitive electronic equipment. Transients are short-duration voltage or current surges that can damage equipment. Flicker is a rapid fluctuation in voltage that can cause lights to flicker. The ability to measure these advanced parameters can be helpful in identifying and resolving power quality problems. When selecting a power monitoring system, it is important to consider the environmental conditions in which the system will be installed. The system should be able to withstand the temperature, humidity, and other environmental factors that are present at the installation location. Some systems are designed for indoor use only, while others are designed for outdoor use. It is also important to consider the security of the power monitoring system. The system should be protected from unauthorized access and tampering. Data should be encrypted to prevent it from being intercepted by unauthorized parties. Access to the system should be controlled by password or other authentication methods. In addition to the technical aspects of power monitoring systems, it is also important to consider the business aspects. The system should be cost-effective and provide a return on investment. The cost of the system should be weighed against the benefits of improved energy efficiency, reduced energy costs, and improved power quality. The system should also be easy to use and maintain. The user interface should be intuitive, and the system should be reliable and require minimal maintenance. By carefully considering all of these factors, you can select a power monitoring system that will meet your needs and provide a valuable return on investment. Ultimately, the goal of a power monitoring system is to provide you with the information you need to make informed decisions about your energy usage. By understanding how much energy you are using, where you are using it, and how efficiently you are using it, you can take steps to reduce your energy consumption, lower your energy costs, and improve the sustainability of your operations. The data acquired from power monitoring systems provides insights into how to optimize energy consumption. By observing the patterns of energy use, you can discover energy-saving opportunities. For example, you can identify equipment or processes that are consuming excessive energy and make adjustments to reduce their consumption. By analyzing power factor data, you can identify the need for power factor correction to improve efficiency and reduce energy costs. Power factor correction involves adding capacitors to the electrical system to reduce the amount of reactive power. Power monitoring systems also provide valuable data for preventative maintenance. By monitoring the performance of electrical equipment, you can identify potential problems before they cause a failure. For example, You can monitor the temperature of motors and transformers to detect overheating. By detecting problems early, you can take corrective action to prevent equipment failures and avoid costly downtime. In summary, the adoption of an Ethernet-based power monitoring system is a solid step to managing power consumption.